Um, okay, well, on that note, so let's begin with one example, which is solving differential equation y prime equals 2x y squared. And then we're going to find the interval of solutions. Find solution interval. So the first thing is that let's just solve this differential equation. On the right-hand side, we have this 2x times y squared. Looks like the function of x times the function of y. So I can try to use separation of variables. So use separation of variables. So I'm going to rewrite the differential equation as dy dx equals 2x y squared. Divide by y squared, move dx to the right, so I get 1 over y squared. Dy equals 2x dx. Now I can integrate both sides. If I integrate the left side, I have integral of y to the negative 2 dy. The right side, I have integral 2x dx. I think both sides are manageable, right? So if we integrate y to the negative 2, so I get negative y to the negative 1. The right-hand side, I have x squared plus c. Solve for y. Divide by negative 1, so I get y to the negative 1 equals negative x squared plus c in parentheses. Flip both sides, so I get y equals 1 over negative, but I'm going to put negative 1 in the numerator, so I have negative 1 over x squared plus c. You can keep it in the denominator, but it's just kind of preference. Any questions? So this is the solution, the general solution, because we don't know what c is. And the solution is in the form of y equals a function of x. So this is the explicit form. Okay, so how do we find the interval of x value that will make this function valid? What do we do? How do we find the interval of x? It's really just, so normally when you find the interval of x, you really just look at the solution as an n. You try to figure out, okay, which x value can I put in there, which x value I cannot put in there. In this case, because it's x is in the denominator, so we really just have to be careful with the denominator, not 0, right? So, to find the solution interval, we have to make sure that the denominator, x squared plus c, cannot equal to 0. And solve for x from there, so x squared cannot equal to negative c. Take square root on both sides, so x cannot equal to plus minus square root of negative c. If you look at the number line, suppose that's a 0, so negative square root of negative c is to the left, positive square root of negative c is on the right. So basically we have all the numbers except for those two values for x. It could be this part, it could also be the middle or to the right. Those are the three intervals. So at the end, the solution interval, or possible solution interval, it's going to be negative infinity to negative square root of negative c, or we can have between those two values, negative square root of negative c to positive square root of negative c. Maybe the interval on the right, square root of negative c to positive infinity. So that's three intervals. One of them could be the solution interval for this function. We don't know which one, so we just list all of them. If we want to know exactly we want to know which interval it is, We have to know the initial condition, but we don't have the initial condition here. Any questions about finding the solution using separation of variables or finding the solution interval there? No? Okay, so let's kind of change the question a bit. So suppose we still have the same differential equation, y prime equals 2xy squared, and here we have a initial condition which is y of 0 equals 1, and we want to solve the equation for y, and also we want to find solution interval. It's very similar to what we have been doing, except that now we just have an initial condition we have to take into account. I'm not going to solve the differential equation. I'm just going to take what I have, right, to save time. So recall that we had y equals -1 over x squared plus c. I'm going to apply the initial condition to find c, so that will give us 1 equals -1 over 0 squared plus c. That gives us c equals -1. The solution is y equals -1 over x squared minus 1. This is a solution that satisfies the differential equation and also initial condition. I didn't do it from the beginning. I just kind of take what we had earlier to save time. Any questions? And we have to find the solution interval for this solution, right? We want to know for which x value is this solution going to be valid for the differential equation and the initial condition. Well, we can follow what we did earlier. So we know for sure that the denominator cannot equal to 0. And if we solve for x there, x squared cannot equal to 1, x cannot equal to plus minus 1. That will give us -1 and a positive 1. Those two values we have to exclude. Well, you probably wonder, wouldn't that give us three intervals again like we had before? -infinity to -1, -1 to +1, +1 to infinity. The answer is no, we don't write down all three of them. There's only one interval that we have to include. So in this case, the solution interval must include the x value from the initial condition. And then the x value is 0, right? So the interval that we take for the solution must be including x equals 0. So this is the only interval we're going to have from -1 to 1. So the solution interval for this problem with initial condition is only going to be from -1 to +1. It's not going to have this part, it's also not going to have this part. So that's the difference between a problem knowing the initial condition and don't know the initial condition. Any questions? I hope that's not confusing. It could be. When I first looked at it, I was kind of a bit confused. Any questions? You had a whole bunch of questions in the homework that was asking you to find the solution interval. Some of them you don't know the initial condition. You kind of just leave it with a constant c. Write down all the possible intervals. Some of them you can actually find the specific one. All right. I'm not hearing any questions, so any questions from the homework? If you, go ahead. Oops. Okay, does that kind of clarify it?
Yeah.
It's just kind of basically at the end you have the function, right? Y equals some function. Basically just look at what the x value can go in there, what x cannot be there to make the function valid. Yep. Which one? 8? Oh, okay. So this is the question number 8. The one about COVID infection. Any particular part? No. Okay. So here, so basically, it tells you that the number of infections is basically follow this growth rate model dy dt. But then it tells you what the solution is, right? Which is y of t equals c e to the kt. And they tell you the two values. One is on March 5th and then another date, the 7th. So on the 5th, there's 184. On the 7th, there's 403. So I'm assuming that t here is the date. So t represents the number of days. It says use this data to determine the constants c and the k. You can take March 5th to be t equals 0. So this is t equals 0. We have y equals 184. And then that's the 5th. So 6, 7, March the 7th is t equals 2. Does that kind of make sense? And we're just going to use those two values put into the equation. So I'm going to plug in the first number. So I get 184 equals c times e to the k times 0. Oops. And to plug in the second number from March the 7th, so I get 403 equals c times e to the k times 2. And I believe, I don't have the value, but I believe the first one will tell you c equals 184. And you can put in there and then solve for k. Is it okay if I kind of stop there? Yeah. Okay. And that will give you so after you find c and the k, you can put into this function y of t, and then that will allow you to find d, because you kind of just have to count how many days from March 5th to April 1st. And then also for this one, if you know this number for y, then you can figure out how many days for c. And I think if d, you kind of have to explain a bit. Not a lot, just a little. Any other questions? 7? Okay. 7 is a very good question. That the question is asking you to do is not solving the differential equation, but using the initial condition to plot the solution curve that satisfies the initial condition. I'm going to take this middle one. For example, you can work on the first and the last one. So this one says the initial condition is when x equals 0, y equals 0. So we can start that point, 0, 0. And I don't know what the solution looks like, but I know that at various points, I know the curve has a slope corresponding to those arrows. So what I'm going to do is I'm going to start this point and then kind of just trace a curve that has a slope matching the arrows next to it. So starting that point, and then the first segment is kind of follow this arrow right next to it, and then kind of follow the next arrow. It doesn't have to be on top of the arrow, but the curvature kind of follows the arrow. Well, not really the curvature, the slope at each point follows the slope of the arrow. And then that kind of goes up. And I guess kind of coming down this way. So this will be the curve of the solution. We don't have a formula for it, but if you were to plot the solution, that's what it looks like. You just label this is the solution when y of 0 equals 0. And if you plot the first one, it's going to be perhaps similar. You're starting at this point and then kind of going up and then eventually coming down. And then the other one you're starting at 0, -1, starting at this point. It's not going to be the same state.
So for this, if we're doing that, say like, with paper with waste, or we draw the slope field, or just see what it looks like and then draw the line.
To be honest, I really don't think it's a good use of time to just draw the slope field.
Yeah, so we'll learn like
Unless Professor Gibson is going crazy.
just the general shape.
Just the general shape. But if you want to know the general shape, you do have, and if you can't solve it, you do have to know the slope field.
Right. So I was wondering if I just look at it and then
Like kind of do it online.
yeah.
I would say that's okay.
Okay.
But at least demonstrate that you can maybe just draw a few arrows, like maybe just kind of like plot arrows in this area if I can. And that way you know where the slope field comes from, how to plot it. I wouldn't recommend doing the whole thing. Yeah. Good point. Any other questions? How about number 4? Have you looked at number 4 yet? Is it okay? Number 4? Yeah, good. How about number 6? Number 5 perhaps? Haven't looked at it yet? Okay. Okay. Maybe I'll look at number 4, especially the solution interval. If you haven't done it yet, I'm going to skip. Yeah. So let me write down the question first. So the question for number 4 in the homework is dy dt is equal to 1 minus t plus y squared minus ty squared. So can you tell me what you did in the first step? Excellent. So, so that's a good step. So first step, take out the y squared from the last two terms. You get 1 minus t, stay the same, plus y squared times 1 minus t. And it turns out that you can continue to factor 1 minus t, right? Good. So that will be 1 minus t, 1 plus y squared as a product. So what I did is I kind of treat this as a factor. So I factor out 1 minus t. From here I only have 1 left. From here I get y squared remaining. And the next step is treat this as a function of y. This is a function of t. We can do separation of variables. You get 1 over 1 plus y squared dy equals 1 minus t dt. Integrate both sides. I'm going to let you do it if you haven't. And at the end, what do you get for the solution? What do you get for y? Excellent. So that will be the solution. After you integrate correctly, maybe do a little bit rewriting, and then you end up with that. So that's a solution. To find the solution interval, it's not easy. At least it's not nice to look at. So I wouldn't even recommend to write down the actual interval. Maybe just the condition for the solution. So if we want this solution to be valid, what do we have to do? How can we make this function y equals 10 a valid function?
Break it into sine.
You could do that, excellent. There's a couple ways you could break it into sine and a cosine. And then that will give you a denominator. You can just look at the denominator, see which value you cannot have. That's a good point. You could also just look at the tangent directly. So that's what I kind of being lazy and did. So I just think about, okay, so this is a tangent function. And if I remember correctly, the tangent x graph, y equals tangent x, has a few vertical asymptotes. Well, actually have a lot of vertical asymptotes. If you recall from like a, I don't know, geometry or maybe algebra 2 class, you probably saw this graph, right? And this graph tells you that the x for tangent x function, the x cannot equal to pi over 2, cannot equal to 3 pi over 2, or negative pi over 2, or multiples of pi over 2. Which means that this part, the parentheses part here, cannot equal to all those values. So just based on the graph of tangent, we know that t minus t squared over 2 plus c cannot equal to pi over 2, 3 pi over 2, and all those values. I'm just going to say pi over 2 times 2n plus 1 for all n equals integers. This upside down a means for all, if you haven't seen it before. So what this says is that, so this part inside the tangent cannot equal to all the r multiples of pi over 2, so that's always going to be r number. It could be positive or negative, but it just cannot equal to that number times pi over 2. I would say if you just leave it the way it is, that should be an acceptable answer there for the solution interval. Two n plus 1. So that just means that's going to give us an r number. Could be if n equals 0, that's going to be 1. If n equals 1, that's going to be 3. Or if n equals negative 1, that's going to be negative 1. So it just means that this side is going to be pi over 2 times all the r numbers. And it cannot equal to the parentheses on the left. It's just kind of a short way. If you do want to kind of spend some time try to figure out what the t is, you basically have to move the right hand side to the left. So you get negative t squared over 2 plus t plus c minus pi over 2, 2n plus 1. Treat it like a c here, and then apply quadratic formula to get t from there. So you get negative, so this is a, this is b, 1, this is c. So apply quadratic formula, that will give you the two t values. But that's a lot of t values because the n could be any number. I would say probably just leave it in this form instead of doing a lot of work. Any other questions on the homework? All right. I think I should mention that number 5, just in case when you work on it. Number 5 in the homework, we given that dy dx, of course we solved this. Dy dx equals e to the x plus y plus 3. So I'm not going to show you the first work. I think it's good for you to try to figure out on your own or work with your peers. I do want to point out that if you have x to the m plus n, you can write this as x to the m times x to the n. That will allow you to rewrite this side to separate the x from the y. And then you can do separation of intervals there. And eventually, you're going to end up with y equals negative natural log of negative e to the x plus 3 plus c in a parentheses. So that's the solution at the end, or something looks like that. So for this solution to be valid, there's something that you have to consider is the natural log. That's the key part. If you remember that natural log graph, only going to be on the right-hand side, right? It doesn't have the x equals 0, doesn't give you negative x. Only for x is positive. This is the y equals natural log of x. Therefore, if you want this solution to be valid, this part inside the natural log has to be positive. So to find solution interval, we have to make sure that this, we have to make sure that this part is positive. It cannot be 0, cannot be negative because of the natural log there. And that just becomes negative, parentheses, e to the x plus 3 plus c greater than 0. We can divide by negative 1 on both sides. That will give us e to the x plus 3 plus a c. It's less than 0. We can move the c to the right. That becomes e to the x plus 3 less than negative c. Now, how do we get x out of here? It's the inequality. We could take the natural log on both sides here to get rid of this base e. The reason we could do that is because the natural log is the continuous function, it's an increasing function. So if the input is smaller, then the value will be smaller. If the input is bigger, the value will be bigger. So just add natural log to both sides. We get x plus 3 is less than natural log negative c. And there you can solve for x from there. So x is less than natural log negative c minus 3. So the interval will be from negative infinity to whatever that is. Well, right here. I mean, this whole thing. Definitely give a try. I think if you are careful enough, you should be able to figure out what the y is. And take a look at the solution interval I wrote, see if it makes sense. Questions? It's due Sunday, so you still have time. If you have more questions, feel free to ask me tomorrow or just work with each other in the class. I believe that you have to kind of show your own work, so don't just write down answers from someone else. So definitely try to, make sure you understand how to do the question, I guess. You can work on it together, talk about it all the time, doesn't matter. It's just that at the end, on the exam, you're going to do it yourself, right? So. No questions? All right, let's move on to the last part. It's hopefully we can finish a little bit early, but I'm not sure. Probably just finish on time. I know you all want to go, but let's talk about this last part. It's a new group of differential equations that we can solve, but it requires a different technique. So this is what we call a linear first order ordinary differential equations. It has the form of y prime, the derivative of y, plus p of x y equals f of x. So this is a little bit different from what we had before, which is y prime equals f of x g of y. right? So we cannot really write this as a product, even if we move this to the right hand. So the separation of variables doesn't work here. So what do? To solve this, we're going to use integrating factor R of x. This is a new technique, a little bit different. So how do we use this integrating factor? So what we do first is that we take the differential equation, we multiply by R of x. So we get R of x y prime plus R of x p of x y equals R of x f of x. We just multiply the differential equation with R of x. There's some function, we don't know what it is. And then what we're going to do is we're going to basically write a new equation following this pattern, except for the middle term, the other two terms are the same. So the new equation we write is R of x y prime plus R prime y equals R of x f of x. So we're basically saying, okay, instead of writing R of x times P of x, instead we write R prime. So that's kind of like the substitution if you think about it. So what this tells us is that the derivative of R is equal to R of x P of x. You can just write R times P of x. We're basically just saying, okay, whatever this product is, I don't know, but I'm just going to call that the derivative of R. All right, what's the benefit of this? Well, the benefit of writing it this way is that if you look at those two terms on the left, does that look familiar? When was the last time you saw that expression? Well, maybe let me delete this R of x, just leave the R there. The product rule, right? If you remember, the product rule says, I don't know what notation you were familiar with, it was like the function of f of x times g of x, the derivative becomes f prime g plus f g prime, right? So that's literally what this is. This is like f g prime plus f prime g. Right, so that's just the one side of the product rule, which allow us to rewrite the left-hand side as r times y prime, the derivative of the product of r times y. And the right-hand side, which is still the same, r of x, f of x. And why do we do this? Well, there's an advantage of writing it this way, because the left side we have a derivative, the right side we have a function of x. That means if we integrate it, we just are basically finding the antiderivative there. So the product of r times y is really just the integral of r of x, f of x dx, the antiderivative. And then we can divide by r to solve for y, so y equals integral r of x, f of x dx divided by r of x. That's how we find this y. Well, you're probably saying, okay, we still don't know what this is, right? We add this r of x, but we don't know what it is. We can find it on the side here. Because we know this relationship by when we write down this third line. So let's use this relationship. Which is, I'm going to rewrite it, that's a dr dx equals r of x, I'm just going to write r there, p of x. And we can solve for r of x here by using separation of variables. So that's a 1 over r dr equals px dx. Integrate both sides. So we get natural log absolute value of r equals integral p of x dx. Add a base e, so we get absolute value of r equals base e. In the exponent we have this integral p of x dx. And if you recall that if you have a base e, that's going to be positive. So we can actually drop the absolute value sign. It turns out that this integrating factor r of x we added in the beginning without knowing what it is, it's actually depending on the p of x in the middle term. So this is the integrating factor, which depends on what this p of x is right there in the middle. So you could, in the future, you could just memorize this expression for r of x, basically integrating p and add a base e, so that's for r of x. You use it directly in here. Or you can just leave it the way it is without knowing what r is, and you kind of just follow along and find it, and go back there. I'll show you an example. I do want to point out that if you want to use this technique, you have to make sure that there's nothing in front of the derivative. There's only one there, so you can't have like something other than one in front of the derivative term. All right, on that note, let's use one example. Hopefully it will kind of clarify the confusion here. And I'll try to explain step by step. So the example is, we're going to solve the differential equation 1 over x dy dx minus 2 over x squared y equals x cosine x for x is positive. Don't worry about the condition at the end. Let's just solve for y there. So if you remember what I said earlier, I put a star there, so we don't want anything in front of the derivative, right? So here we have 1 over x, we have to get rid of the 1 over x first before we can do anything using this approach. So let's multiply by x on both sides to simplify the coefficient of dy dx. So that just gives us dy dx equals, minus 2 over x squared y times x. That's going to be 2 over x y. The other side we have x cosine x times x. That's x squared cosine x. Are you okay with what I did? I just basically take every term here and multiply with x to get rid of this. And then the next thing I'm going to do is, I really don't like this dy dx. I'm just going to put a y prime there. I prefer to use that notation. So y prime is equal, minus 2 over xy is equal to x squared cosine x. So now we're actually going to use the technique involving integrating factor. So we're going to multiply r of x on both sides of the equation. But to make it easy to write, I'm just going to multiply by r. But hopefully you understand that when I see multiply by r, it just means r of x. It's not a constant here, it's a function of x. So that will be ry prime minus r times 2 over xy equals r times x squared cosine x. And the next step is take that equation, but rewriting it in the middle term. Instead of writing down the whole thing, we're going to use positive r prime y. The first term always stays, the term on the right always stays. So we get ry prime plus r prime y. It's literally just writing the product rule part. That's going to equal to rx squared cosine x. And by writing in this way, we know what the derivative of r corresponding to, right? Let me highlight. So this derivative of r is corresponding to this expression above with a negative sign. And I'm actually going to note that on the side. So note that r prime is equal to negative r times 2 over x. When we line up the terms correctly. So we kind of just set the derivative equals that part. I'm going to write down one more line on the left here, and then I'm going to jump to the right side. So the equation on the left really becomes the derivative of r times y on the left is equal to, let me line up correctly, is equal to rx squared cosine x. Any questions about what I did there? So basically, all we did is we multiply by r, and then we kind of rewrite the second term, then we rewrite both terms on the left to get to this point. Let's just leave it there for now. Let's work on this side to figure out what the r is. So here we have dr dx on the left is equal to negative r times 2 over x. I'm going to use separation of variables. Move the r to the left, so we got 1 over r dr. Move dx to the other side, I got negative 2 over x dx. Don't worry about the left side, we're just going to leave it the way it is for now. Integrate both sides. So I get natural log absolute value of r is equal to negative 2 natural log. Negative 2 comes outside, then it's 1 over x dx, so that's a natural log of absolute value of x. You probably want to add a constant c. In fact, we don't need to add the constant c here, because if you add a c at this point, eventually that c will be absorbed into the constant on this part when we try to integrate. So we just don't write the c there. You could, but it doesn't make a difference. And solve for r there, so we get absolute value of r equals base e raised to the negative 2 natural log absolute value of x. The next step might be a little bit confusing when I'm trying to simplify this side. I'll take a step and try to make it clear. So this is positive, right? So we can plot the absolute value on this side. So we get r equals e raised to the, this is what I'm going to do. I'm going to switch the order of negative 2 and the natural log, so I'm going to put negative 2 behind the natural log. So I have natural log absolute value of x times negative 2. Kind of just flip the order of the product. And I'm sure you all know what this part is, the one I'm boxing in blue. So e to the natural log absolute value of x, e and the natural log cancels, you just give us absolute value of x. So this becomes absolute value of x raised to the negative 2. The reason we have a negative 2 in the exponent because we still have this negative 2 in the exponent. We just work on this part first. And then with absolute value of x, negative 2 stays. And just keep writing. So that's 1 over absolute value of x squared, which is the same thing as 1 over x squared. Because that's the positive number squared, this is the square of any number is going to be positive, so those two are equivalent. So that's what R is. We figure out that R is equal to 1 over x squared, R of x. We can actually use this here. I'm almost done. Just take like probably 30 seconds. Before I do that, any questions about what I did solving for the R of x on the side here? Separation of variables is the key. You're pretty much always going to have to, have a natural log, and then you have to add a base b. So those kind of like the standard process, and then simplify really. So after we've done that, we take this R function, put it in the equation on the left. So that will become 1 over x squared y derivative is equal to 1 over x squared times x squared cosine x. And the x squared cancels, so we just have cosine x remaining. The left side is the derivative, the right side is cosine x. If we want to solve for y, we just integrate. We're basically finding the antiderivative of cosine x. So we get 1 over x squared y equals integral cosine x dx. What is that? It's the antiderivative of cosine x. Sine, right? Plus c. And then we can solve for y. Y equals multiplied by x squared. Y equals x squared sine x plus c x squared. So this is the solution. The reason we have cx squared is multiplied by x squared to both sides. X squared times sine x, x squared times c. Any questions? I know it's a new material, and I'm pretty sure you're going to talk about this tomorrow in the lecture. But it's good to know. And we're definitely going to, I suppose we're going to spend more time on this next time. All right, take care, and good luck on the homework. Take care, and just stay warm and stay healthy.